Next, we consider a new class of materials with additional level of complication or sophistication. So we are going to talk to materials with two characteristic directions, right? So we just consider the case when material is reinforced by some fibers that are aligned in one direction, so that can manifest in this transversely isotropic type of behavior, but so we are not limited to such situation when we align all the fibers in one direction. In engineering materials, it's quite a known situation when you can have different orientations of fibers. So some that will be oriented in one direction, and the other, let's call it a family of fibers, so the two families of fibers and identified by their alignment direction. So that the other family of fibers will be aligned in different direction. And for that we have its own vector, orientation vector, which we just here this tag tag 0, and 0 again indicates that we're talking about the direction in the antiform configuration. Now, so in engineering materials again, so that will be very relatively simple situation. Then schematically we have one direction of fibers identified with, let's call it M0 as before, and then we also can have other direction. Let's use blue for that. And the angle between them is arbitrary here, so that is not necessarily identified by anything. And again, so in the different direction, let's just tag here. So again, engineering materials can be quite popular to put some fibers in one direction in one layer, then they have another layer with other fibers aligned in the other direction. We can repeat these layers, and overall we can have some homogenized response of that material that will have quite good strength against tensile loadings in the direction of fibers, and when they applied in this direction and applied in this direction, and they also will contribute somewhat to other direction. In that way we produce a quite quite good reinforcement. And so that's if again fibers are stronger than the matrix, so that fibers contribute to reinforcement of that material. Now, so some of the motivation for us to look into the behavior of soft materials with such microstructures, some typical organs that scientists try to model and understand how we can provide some meaningful material law for these materials. And somewhat good examples, and that again for motivation, was this consideration of the arterial walls. So we're now again shifting back from engineering materials into the natural soft materials. So here the artery, and so and it appeared that that the arterial walls also can be considered. Of course, there is quite different layers with different functions that build up the arterial wall. Some of these layers, let's say, has very little to do with the mechanical performance of the arterial layer, I mean elastic performance, but rather needed for connectivity and for fluid mechanics issues that because, well, of course, consider this as a pipe and there's blood that flowing here. But the structural, the material that actually has elasticity can be considered somewhat approximated by having fibers that reinforce the matrix, and they can be considered as having two preferable directions. This is, of course, an approximation. Okay, so let's say we just take a segment of this arterial wall, and I put it in here, and it's a segment, and so we'll have fibers that will be mostly, and it's point word for the arterial walls, that mostly will be aligned in two directions. So and we can identify them as M0 and M0 tag. Of course, this is in nature. It's never the case that all the fibers aligned in, the majority of them align one direction, the rest is another. Of course, there is somewhat a dispersion curve, and if you measure all the orientation, so you will find basically the distribution something like that, and these two peaks in the distribution and how frequently they appear in the measurement will correspond to the orientation of that vectors M0 and M0 tag. But again, so this is this provides a good justification for us to consider materials with two characteristic directions. So we identify, so we'll just say, all right, so let's say that the majority of the fibers are actually located in this direction and that direction. They provide the function, the elastical function, elasticity of the arterial walls under the conditions that they experience, and basically that would be the inner pressure that we apply here because of the fluid of the blood that is applied here, right? And the arterial wall will deform, and so then we would like maybe to know how this process is happening, and what and can connect these orientations also with the properties and the overall mechanical behavior and deformation of arterial wall under different pressures applies here. So we will look into that example in more detail, but at this point we're going back to the basics, and we of course remember that we to model such material, so now we need to introduce an energy function, so we need a constitutive flow. And you can find this type of situations of not inhomogeneous behavior, having some fibers that embedded in, can be also considered as embedded in softer matrix and different organs, and also a heart as mentioned here. So there are different alignments that will also be different orientations, and that is quite a common situation of having the mixture of fibers in matrix in soft biological tissues indeed. Now, all right, so for a moment we again forget a little bit about the motivation and just strictly deal with the mathematics of that. Yeah, and here so we have our common strain energy density function, and which has now additional symmetry group, let's say. So now it becomes invariant for a different group of rotation, let's say. So now so there is one orientation that restricts that, and the other orientation that also restricts that, and hence basically to the previous consideration of what we already had. So we have this additional term that basically is governed by the orientation of that second orientation of that second family of fibers that we introduced. And therefore, so when we had only these guys sitting here, basically, so the first that is common for so this is isotropic elasticity, no fibers, and so now the second one with them so this is the first orientation here. So this is just one family of fibers, so just all the fibers aligned in one direction. And now we can say that we basically added additional fibers, if you like, and so they are now aligned in a different direction, M tag here. So, and for this case, to model isotropic elasticity, so we needed, so if we now want to model so this invariance, the energy function want to express it in terms of invariance. So for this case, for the isotropic elasticity, we only had 3, Then when we had this fiber, we actually had 5. We need to add additional 2. And now, very interestingly here, as we add additional family of fibers, we need to have additional 4, from which 2 will be basically in similar structure as this that we added here, but now we also have somewhat an interaction, a mixed invariant that will also include M0 and M tag. So that is additional structure, combination for this so-called structure tensors. So we have additional 4 invariants. So maybe a little bit counterintuitive, as we only had additional 2 invariants from the consideration of one family of fibers that we added. But now we have combination of these 2. So we have 2 that come from here, 2 that come from here, and additional 2 that comes from the mix. So the total will be, in this case, is 9 invariants that we would need to fully describe it from strictly mathematically speaking. And so now we have this 4 additional invariants, right? So that is, and to express them, you will see that the following, so I6 and I7 basically they are almost the same as we would say for I4 and I5, right? With only difference being in that you have here these dots represented M tag instead of M0. So just they're exactly the same. They just for different structure tensor. This the tensor product M0 tag, the tensor product of these 2. So these 2 additional ones, and then here you start to notice that there is a so the I1 and I9 represent the somewhat mixed, let's call mixed structure tensor, right? So we have one is from one family of fibers and the other is for the second family of fibers at M tag 0. And then we have that I1 somewhat strange invariant that if we look a little bit closer into that and try to analyze further whether that invariant would contribute anything into the stresses. At the end, we want to establish the connection between stresses and as function of the deformations that we apply. So that's basically what is the constitutive law. But then if we look into that I9 and try to recall that where this the contribution of stresses come from, so then we will at certain point we will need to take the derivative of that invariant with respect to some strain measure, and you can see that the invariant is not dependent on the deformation, so it's purely the orientation. So hence it will not contribute to stresses, and basically we don't need to drag it with us. So that's as we derive the responses in terms of stresses. And very similar to the tensors that we already to the vector M0 that we considered. So when we apply the deformation gradient f on that vector M0 tag, so basically, of course, that's basically transformation of that vector into the deformed configuration. So in that sense, that works exactly the same, of course, as for the other family of fibers, the first family of fibers. When we deform it, so it transforms from the reference or undeformed configuration into the deformed vector M. And now, so again, M0 and M0 tag were unit vectors, but I already mentioned that when we transformed into this deformed configuration, in general, they are not unit vectors anymore. They could be still unit vectors, but in general they are not, and they can be stretched. So if you want to normalize them back, so that's also possible. So we need to calculate the length and derive by this factor of stretching. All right, so so to put this into formula, so that's again our formula for 514, and as I already mentioned briefly, that again, the invariant I9 is not really that important for a continuation of our derivation of stresses. Again, so if you take the derivative, if you look that into the invariant I9, you don't see the dependence on the deformation, and therefore when you take a derivative, it will produce zero contribution of that. Now, for us, also very convenient to derive the derivative of the invariant of any of this invariant with respect to tensor C, because then we directly can calculate the stresses by just using our formula like this, and then using the chain rule. So well, we have the derivative of energy function with respect to invariance, which we can specify, and that basically will be our constitutive law, and then we just need to substitute these derivatives of the invariance with respect to C, and then again, so this is our usual drill that we already did. So but here of course we have additional new invariants that we need to deal with. So we want to derive it each time we encounter them, or we just derive it one time and can use these formulas. And of course saying that we derive it and use it, it's probably too much to say. Of course they were derived before us, but the derivative is, as you already have seen, it's pretty straightforward, and we can of course can do this as a small exercise. Obviously the derivative that we need to take here, for example, invariant of 6 and the 7th invariant, we don't really need to work at all, because they will be exactly the same as was the invariant for I4, with the only substitution of these constant vectors M0. So we just basically put here this tagged of the second family of fibers, and that will be the result. And the same also for I5, because they have exactly the same structure. It's just the multiplication here in I5 we had so with obviously with M0, so there was only one family of fibers, but this is just a matter of labeling these constant unit vectors and directions of the fiber. So for the second family of fibers, of course, these two are very similar to this one, very similar to the derivative of I4, and 7 is basically identical to the derivative of the invariant of C. Now for the 8th invariant, so we have two contributions. I don't derive it here, so again this is something that you can do if you like. Take this derivative, but need to be careful with the multiplication, and usually we typically would write this in indexes, in index notation, and see what multiplies what, and then what will happen is that we'll have two terms like that, so with the different order, so the transposed part of this tensor, mixed structural tensor is called in that way. So M0 tensor product M0 dot. And so this is a new one. This is a mixed one. So when you have mixed structural, so the new one and the second family of fibers and the first family of fibers are mixed here in this mixed structure tensor, right? So this is the first family of fiber appear here. All right, so once we have that, so then we can directly write our stresses based on these invariants, in general way, and then we can use all these usual transformations to the first Piola, and then by using the transformation from the first Piola to the Cauchy stress, and that's basically what we want to write. We want to write the dependence of the true stresses of the Cauchy stresses on the deformation in general way. And so for the Cauchy stress, now let's finally just put it here. So you can see once again that I have here a few parts. So the first part is coming from the incompressible material, so it's very familiar. It doesn't really change, and there is no isotropic material. Sorry, for isotropic material. So the first line. So this isotropic elasticity, this didn't change. Isotropic part. So this is right here, right? And so there are no assumption made about the compressibility. Hence, you still have your invariant, our invariant I3 here, and the derivative of that invariant with respect to C, right? So in that, basically, we have here all our three invariants, I1, I2, and I3 contributing into this part. So this is the isotropic part that comes from that, and this is unchanged. Now we have a second part that we already have seen exactly here with when we have one family of fibers, so this transversely isotropic material, and you can see that here we have the terms, the derivatives that comes from the fourth and fifth invariant. So that was a family of fibers that had a structured tensor depending on one family of fibers that were aligned in that direction. Sorry, just M0. Let me just erase that. And so and then the second part here, let's use something like that. So this is the second part that fully corresponds, and that basically you can see that they are almost one-to-one, with only differences is that we are having here this the different structure tensor. So you have this M tag here instead of M. So basically this is another direction of fibers that we express in terms of invariants I6 and I7, and they associated with structure tensors that were built on this additional direction, the second family of fibers, M0, M tag. And so basically you can see in this structure of the stresses that, okay, so if there is no fibers, M0, so there is no contribution from here, so we basically have only one family of fibers, and that will be this line. Or now we have but once we have a combination of those, so we automatically have to have this mixed term here, so that comes as a combination of having both M0 and M0 tag appearing here. Right, so probably should use the same. For consistency, let's use the same colors for the combination of these sources M0 and the M0 tag. No, that wasn't. Anyway, anyhow, so and the M0 tag that contributed to the term that comes with it. Right. So again, very simple structure. So the expression is rather bulky for the Cauchy stress, but a very simple structure, very straightforward. So we have isotropic part, we have the part that comes from the first family of fibers aligned in one direction, or anisotropy, or another preferable direction. They have another contribution of those fibers, and we also have, let's say, the interaction of these fibers, contribution of these fibers as they present in the material together. So that comes with the eighth invariant from that. And now, as usual, we can deal with incompressibility. Basically, the only thing that we are doing with incompressibility is that we need to deal with this term I3, which is equal to 1. And you can see that that doesn't really appear in any other terms here that are related to this anisotropic behavior. It's still a bulk behavior of isotropic response, so it still sits here, and hence this is the only thing that we need to modify. And so, as you can see, this contribution from the fibers on the first and second and third line remains unchanged. So this doesn't change, and the only change is sitting here. So this is our familiar usual suspect of Lagrange multiplier or hydrostatic pressure, and that we replaced the contribution of the third invariant, but of course the structure is multiplied by the identity tensor here in the Cauchy stress, and that works exactly the same way as it would be in just isotropic materials, or in just materials with transversely isotropic, with having only one family of fibers aligned in the same direction. So that incompressibility is pretty straightforward after we dealt with that. So this is very general. Of course, so there can be many energy functions that you can specify, right? So this is in general way. Again, and I remind you that these indexes here denote the derivative of of the energy function with respect to a certain invariant, right? So this is psi 1, so that's how we denoted that. This is not 1 but n, so if it's 1, so n becomes 1, so this will be with respect to invariant 1, 2, 3 and 4, etc. Until 8 in our case. And typically these functions are rather simple, so when we consider the isotropic elasticity, so we have very simple either linear or sometimes quadratic terms that come out from this derivative. Now, to give you an example of energy function that's based on this invariant, we'll just briefly basically show one of the popular energy functions that is appear to be very effective, and this is the energy function due to the three researchers, Ray Ogden, Christian Gasser, and Holzapfel, the author of one of the suggested books. So actually two of them are authors of the suggested books on our course. So the one that Gerhard Holzapfel, and the other is Ray Ogden, and Christian Gasser was a student of Holzapfel. That's a younger. He is yet to write his book for a course like that on mechanics of soft materials. And so basically, so you can see that the structure is preserved, but they did not use all the invariants, and this is allowed, of course. So it's mathematically speaking strictly the structure that you would need, but you have experimental data, and you may see that some invariants don't really contribute much, and they're not that important. As for example, in isotropic elasticity, not that many people are using the contribution that coming from the second invariant, so that becomes a little bit. It becomes much easier if we don't consider that, and still can get reasonable results. And as you can see, so this is the approach that I also taken for the isotropic part. So this is just one invariant I1. And I2, again, so we already mentioned that it's quite common to neglect that and limit to ourselves to a simpler model. So basically have for isotropic part only first invariant, pretty much like a Neo-Okean model. And then for the second part, you have something quite unusual. So first of all, you can see that they used only the fourth invariant, so the terms like that would be here, and the term like that. So there are no mixed term, and and there are only contribution of the fiber in one direction, contribution in the other direction, and without these non-linear terms that can come from that. Nevertheless, so they also introduced an exponent here. So that, again, you can introduce any functions that you like, that you think that will fit better your experimental data, as far as you're consistent with all the assumptions, with all the constraints that we put on the energy function, such as the invariance, certain invariance, but that once you play with the invariance, so you will be fine. So then with appropriate invariant you will be fine, and so of course you also need to say to satisfy that there is no stresses in the undefined configuration and the energy is zero. So but you can use basically any function. You can use logarithm, you can use powers, you can use exponents, etc. So what is good about using the exponent here is that that allowed to capture the behavior. Sometimes it's called a recruitment of fibers, so as we start to deform. So the fibers in nature, well, basically they are not, they cannot really be considered as a aligned straight fiber that is reinforcing the material, but they rather okay, they can have some waviness and some crippling shape. And so therefore when you apply tensile loadings, so initially there will be a range of deformation when they are not straightened, and so therefore they don't really contribute much to the tensile strength of the material, to the tensile stiffness or of the response. But then gradually as they strengthen with deformation, so then they start to strongly show their reinforcement to the matrix, and that's these functions of the exponent allow to capture very nicely. So again, as you can see, these are phenomenological models, meaning that all these constants they don't really have much of the physical meaning. So you have an experimental data, then you go you go with that to feed the experimental data. There is some information that from microstructure for the physical meaning that you embed in this structure, and that's basically will be this direction of this initial preferable direction of two family of fibers that you plug in here. But again, it still remains a model, and as already mentioned, and that was derived explicitly to model arteries, and already mentioned. So arteries had rather distributions of different orientation. So let's say to measure this as an angle of these fibers with more or less. Okay, so I'm exaggerating here, but these peaks may be not that pronounced, not that strongly pronounced as I sketch them here. So and in fact, so it also can be in fact, if you are after more accurate modeling, trying to account to contribution of the fibers that are maybe not exactly aligned into this particular direction, particular angle that associated with the direction M0 tag. So then there is a way actually these guys also thought about that, and so they so introduced a new model, but because there was still the same guys, so they had to change the name of the of this law, the constitutive law. So just by alternating the order here. So that's instead of HGO, so there is a GOH, and the joke here is that they probably need to find somebody that the name will start from D, so then that will be a God model. But jokes aside, so this the new model, they introduced, they substituted these invariants with and similarly structured invariants with the functions that actually include the integrals of over this distribution. So they include the statistics of that, and so that is in a similar structure still can be captured. But again, so we're not in the frame in this course. We are going to go into those details. I just put it here that these things are available, and you can, if you're interested in modeling soft materials with the accuracy and accounting for these features of the microstructure of different fibers, of the fibers distributed in a more realistic manner. So there are models out there, and there are literature on that. And so that's and finally, of course, probably all this discussion would be incomplete with the examples of the energy function without the mentioning the name of Professor Fang, who is very recently passed away, and he's can be considered as the father of the of biomechanics in for soft materials and soft tissues. So there's very important contribution to that. And here I put the just example that of the energy function of the specifications that sometimes refer to his model, Fang model, that has a similar structure to the also uses the exponents. So historically, his group was the introduced this idea of using these exponents. Also, maybe maybe quite a not a super complicated idea, but showed working very well using the exponents to model these the arterial walls. And this is specification for specifically for arterial walls, and as you can see that this is already the green strain components here are already described, so they already written in the polar coordinate system, right? So that is we introduced before, and that we're going to use to look into with more detail. So in the coordinate, when we have an angle here, and we have the radius, and we have the height, so this z coordinate that remains the same. And the difference between the model that we just looked into, that was due Gasser, Holzapfel, and Ogden, right? So here we do have this invariant that come from the structure tensor, and as opposite to that, so this model doesn't really the Fang model specification of that doesn't have this microstructural information, and basically only these constants that are fitted entirely. And so based on some experimental data, so in a way, so this would be pure phenomenological model, while the previous one built somehow on the still being also a phenomenological model, but this one doesn't build on the microstructural of this so-called structure tensor that come from the microstructure. There are of course some alternative ideas of using, and already mentioned probably that using micromechanics directly trying to figure out the properties of the fibers and of the matrix, the orientation and the amount of those materials, and based on that information trying to directly derive the energy functions, and so you don't need to feed anything, but can obtain the information just for imaging of that biological tissue, or if you already work with engineering materials, then you of course know what is the amount of the fibers and matrix that you put there, and you know the properties of them, and then you can tailor and pre-design the effective properties of the material with those mixtures. But again, so it's more complicated matter, especially in non-linear elasticity, this so-called micromechanics-based homogenization, which is this is not the scope in our course, but I'm just mentioning that for the complete picture of the models that are available to treat these types of materials. All right, so next what we will do, we will consider an example of the arterial wall and derive some solutions for that, and see how these stresses distribute and what we can learn from that. Okay, see you then.